This is joint work with Ujjayant Chakravorty of Tufts University, and we're interested in the industrial organization of groundwater. So, a few words about the importance of groundwater. So, more than half of world food production is produced using groundwater irrigation. Half of India's population is still employed in agriculture, and India is the largest user of groundwater in the world. Aquifer depletion is a major issue. There's this recent satellite data, which is a new thing. I mean, we already knew this, but there's new satellite data from NASA satellites which have found major aquifer depletion in northern India. And this aquifer depletion leads to increased poverty and water disputes as well. There is an interesting paper by Sheetal Sekhri looking at eastern UP. She finds that in certain circumstances, aquifer depletion is associated with significant increase in poverty and also in disputes over water. So, a little bit about groundwater versus surface irrigation. So, something like 70% of Kharif acreage and 3/4 of Rabi acreage is irrigated by wells and tube wells. So, that's a lot of the cropped area which is irrigated by groundwater. In addition to that, the productivity of land that's irrigated by wells is much greater than the productivity of land that's irrigated by surface water on average. And the reason for that is to do with groundwater. You have much better control over the timing of irrigation, whereas with surface water, usually in India, most of them are large canal systems, and so the farmers don't control when the water comes in. It's controlled at a higher level. So the result is that basically that groundwater is even more important than these numbers seem to show as far as crop output is concerned. And as we know, in many areas, including the northwest and also in the southern peninsula, it's getting rapidly depleted. On the other hand, if you look at surface water, there's this study by S. Duflo and Rohini Pandey on dams, and they find that being in a district that's irrigated by surface water increases production, but not by very much. In fact, what they found was that if you looked across India using NSS data put together with data on dams, what they found was that if you look at downstream districts, there's a fall in poverty in downstream districts that have dams, that have irrigation from surface water from rivers that are dammed. But there is a corresponding increase in poverty in upstream districts, essentially because you've disrupted the hydrological situation upstream and people have been displaced and so on. And the effects of all of that in terms of increased poverty in upstream districts more than outweighs the reduced poverty in downstream districts. So, surface irrigation has its problems. And that's just to sort of say that once more to emphasize the importance of groundwater. So, a little bit about the institutional structure. In nearly all Indian states, electricity for irrigation is unmetered. West Bengal is an exception. I'm not sure whether there are any others. If it's unmetered, that implies that the marginal cost of pumping is zero, right? So, you pump another, well, that's not quite correct. I mean, there's still wear and tear and so on. But at least the cost of fuel, the cost of the energy for pumping is zero. So, farmers basically pay a flat rate according to the horsepower of the pump, but they don't pay for the quantity of water that they use. So, the marginal cost of pumping is well, if not zero, pretty small. On the other hand, if you're talking about diesel pumps which are used in shallow wells, then of course that has a positive marginal cost, even though diesel is subsidized, but still. I don't want to go into too much of the detail about this because there's a theory paper. It's just motivation. Another thing that I want to emphasize is that there's a lot of buying and selling of groundwater for irrigation between farmers. So, in some regions like Bihar, for example, about half the large farms buy water. Another point is that the pump is typically needed for about 250 hours, but can operate for much longer, and so farmers will pump a lot more water than they need and sell it to other farmers. So just roughly, this is the aquifer picture in India. In the north here and here you have alluvial aquifers, which basically means that they are shallower and they are easier to reach. And in the south you have hard rock aquifers, in which are more confined and which are harder to drill into and which have less water typically. Groundwater is also very important in China, and groundwater markets are also important in China. So in China, groundwater is used exclusively in the North China plains, and it's about 68% of irrigation. And there's been a shift from collective ownership of tube wells to private. And in China, unlike India, electricity is metered, so the marginal cost of pumping, even from those from wells which are driven by electricity, is positive. And there are water table declines in the North China plain. So a survey found that 70% of households depend on groundwater and 20% of them buy. Areas which are dependent on groundwater have very high population density. This is the North China plain we're talking about here. And that's the aquifer system of the North China plain. This is the major river, the Yellow River, coming into the sea here, and this is the aquifer, which is quite deep. You can see this area. This is a GRACE satellite image showing groundwater decline in northern India, and you can see that here this area is severe groundwater decline with somewhat less severe surrounding into Punjab, Haryana. Okay, I don't need this. You guys know all this. Okay, this photograph I just wanted to point to just quickly. So when the water comes out of a pump here, then it's delivered to fields through these kinds of channels. And we see that there's a very large increase, as you can see here. We are much more dependent on groundwater now than, or this was 10 years ago. Here the last data point, than we used to be, right? So this is tank irrigation that is increased somewhat. Those are also surface ponds in southern India, and this is canal irrigation. About the economic theory, there's quite a bit of literature on groundwater markets which focus on groundwater as a common pool resource and on the dynamics of pumping, basically looking at the groundwater stock as a capital asset and then looking at the depletion of that capital asset, optimal depletion and so on. So there's quite a large literature on these kinds of things. That's not what this paper is about. What we're interested in is really more modeling groundwater markets and understanding how it is that groundwater markets work, because we can't really think properly about policy to address depletion and equity and other issues unless we have a reasonable model about how the markets of groundwater work, given that groundwater markets are extremely important. We are interested in the fact that groundwater is spatial, so you must deliver locally and you can price discriminate. And then in the second part of the paper I'll come to issues of depletion, but in the first part of the paper I'm just going to talk about the first part I'm just going to discuss a static model, okay, which just looks at the organization. These are basically the questions addressed. So is the number of wells, actually this should really say is the well density, okay, we use number of wells in the model, but it really is meant to represent well density. Is the well density appropriate, socially optimal in a static model which doesn't take depletion into account? What are water prices? What instruments does the regulator have? What is the effect of depletion and extraction costs on well density, on entry of cellars and well density? There is some very sparse literature on this. There's a literature on spatially differentiated pricing. Consumers have different preferences and brand loyalties. This is in IO. And there is a paper here which is on price discrimination with location and the inelastic demand. And so this one is related to what we do. Okay, so what's the model? So we just begin with a simple static model. And in this model, our model is basically static, but we look at the depletion issue at the end. Okay, so the way we model it is that we have water cellars along a circle of unit circumference. Okay, so these are sellers, and so sellers means owners of pumps that can pump water and sell it to other people. And so the number of sellers n is going to be, because this circle is taken to be a unit circumference, the number of sellers is the number of wells per unit length here. Okay, it's a one-dimensional model which is meant to capture, of course, a two-dimensional world, but that's just an abstraction to make the modeling convenient. So really the number of wells is the crucial parameter that we're interested in, one of the crucial parameters we're interested in, one of the crucial variables we're interested in, I should say, not parameters, one of the crucial variables we're interested in, and it's the well density. So what's the model? The demand for water, there's some demand function for water from any farm at any given location. So a farm is just a point on that circle. There are n evenly spaced suppliers of water. Okay, so we assume that the sellers locate evenly around, the n sellers locate evenly around the circle. The average and marginal cost of pumping a unit of water is C, rupees per liter or whatever, rupees per cubic meter. The unit cost of transporting a cubic meter of water is T. So where is that cost coming from? That cost is coming from that picture I showed you, those channels, right? So if you want to get the water out from where you get it to the surface, to the pump, so the C is the cubic meters, rupees per cubic meter of getting water from down underground to the surface. Okay, that's the operating cost, the cost of operating your well and pump. And then when you get it to the surface, you have to deliver it to the farm. And when you deliver it to the farm, as you saw, you're going to deliver it through those channels, and so you're going to lose some water due to seepage and evaporation along the way, right? So there's going to be some cost. And we simplify by modeling this cost as constant, even though it's probably not constant, but we just abstract away from it. So the marginal cost of pumping a unit of water and delivering it to a buyer at a distance x from a well, x is the distance from the well to the farm where the water is taken, it's C plus Tx. This diagram is really essential for the whole thing. So the wells are located at A and B, okay. Farms are located in a continuum along this. This thing is a segment of that circle. The marginal cost is here depicted on the vertical axis. It's C at the wellhead, right? And this is x, distance from A to here is measured, that's x along this axis. So C plus Tx is this line basically going up to there in both directions, right? That's the cost per unit. Seller B's cost of delivering, on the other hand, proceeds in this direction away from his well, right? It's increasing like that. And since there are n wells, the distance from A to B is 1 over n. Right? And so the midpoint here, the distance is 1 over 2n. And therefore, this level here, the cost at this point, the midpoint between the two wells is C plus T over 2n. C plus Tx, where x is 1 over 2n. Right? And it rises up to C plus T by n over here. Okay, so we suppose the monopoly price is at least C plus T by n. Right? So in other words, I'm assuming that the maximum price that a seller would want to charge, taking the demand into account, exceeds this level. So in other words, each seller is constrained by the fact that the neighbor can deliver water at his well at some cost which is lower than the monopoly price he would like to be able to charge. Okay, so then the first result that follows from this, which is easy to see, is that the price of water must be decreasing in x. So the further away you get from a well, the less you're going to price the water at to the farmer at that distance. The closer the farmer is to you, the more you're going to charge him. And that's different from the textbook linear city model, for example, where prices increase with distance. And the reason that this happens in this situation is because basically sellers can price discriminate based on buyer location, right? And your incentive, the reason they're evenly spaced on the circle is because the incentive is to locate as far away from the competition as possible. At each location X, basically there's Bertrand pricing. right? So at each location X, what is happening is, to go back to that diagram, you take a point like this, take a point X here, right? Who's going to be selling water to the farm at this point X? The cost of delivering water to this farm from B is at this level, right? Okay, the cost of delivering 1 unit of water to this farm is at this level from B, but from A it's less. What will the seller at A do? The seller at A will charge just slightly less, epsilon less than this price, right? And that will ensure that it's not worthwhile for B to sell water to the farm at this location. Okay, so that's the sense in which it's basically Bertrand pricing. At each farm there are 2 potential sellers, they have different marginal costs, right? Therefore the price is going to be the higher of the 2 marginal costs, right? And the entire market is captured by the seller with the lower marginal cost. So that seller makes a profit per unit of water sold of this distance, which is the difference between his nearest competitor's marginal cost and his own. Okay, and that's why the price line, therefore, is basically following this. It's the blue line here, right? Right at my wellhead, this guy is furthest away, and therefore I can price all the way up to there. As I go further away from my well, it's costing me more and more to deliver water, but that's not what's relevant to the price. What is relevant to the price is that it's costing my competitor less and less to deliver water as I go further away from my well, therefore closer to his, and therefore I'm forced to bring my price down. So there's, as I said, Bertrand pricing at each location X. Okay, what happens when new farms, so of course each seller in this model is making profits, right? At every farm except only this farm is a seller not making a profit, because over there he is forced to price at marginal cost. Okay, what happens when there's entry? Well, if somebody enters, they're going to enter, the best place to enter is furthest away from the other 2, the existing wells A and B, existing sellers A and B. So somebody will come in at this midpoint M. If they come in at this midpoint M, then their marginal cost curves are these 2 lines, and now you get prices are going to fall. They're going to fall from this blue curve to this red curve, essentially, in the same way when there's entry, right? Which means prices are going to fall and profits are going to decrease, right? And the buyers of water, of course, are better off. Okay, so essentially if you have small n, then you have this kind of price path is like this, and if you have a bigger n, then the price path looks like this. Okay, so now I want to look at the case of fixed wells with perfectly inelastic demand. So what do I mean by fixed wells? I mean that I'm assuming that the major cost of, so there's a fixed cost. So what we assume, what I haven't talked about yet, I suppose I better talk about it now. I assume that there's a fixed cost of digging a well and installing a pump, right? Getting an electricity connection, whatever you need to do, whatever those costs are. That's some cost which is F rupees for 1 well. So I want to talk about fixed wells. So I'm going to assume that first in this case, and I'll deal with this rather briefly, is the case when a lot of that fixed cost is actually into digging the well. It's not in the other things such as buying the pump, installing the pump, getting the electricity connection and those things. Okay. What that means is that when new sellers come in to the market, right, and dig new wells, you can't shift your well to some other location to adjust optimally, right? Because if somebody new comes in on one side of you, right, you want to move away from him towards your more distant neighbor in order to capture more of the market, right? So that's what you would do if it didn't cost very much to move the well. If most of the fixed cost was in the pump and the licensing and other things, then that's what you would do. But if most of the cost is in actually sinking the well, then you're in this case. Okay. The other thing that I'm going to consider for the moment is when the demand is perfectly inelastic, right? So it's not price sensitive at all. Every farmer wants a certain quantity of water, and they're willing to pay up to some limit price for it. So what is the seller's revenue? What's the expression for a seller's revenue? The profit of one seller when there are when the well density is n. What's that equal to? Well, it's equal to the quantity of water sold when the price is x at location, when the price is p at location x, right? This is the demand q as a function of price, and the price is a function of the farm location x, and this is the markup per unit of water sold. You sell it at this price, and that's how much it costs you to deliver it to location x, right? And that's it for each farm x, and you're going to sell to farms on either side of you, x running from 0 to 1 over 2n, right? So times 2, because on both sides. A seller's participation constraint saying is basically that the profit that he gets from this has to at least be equal to his fixed cost, otherwise he's not going to bother. Okay. So equilibrium then is given by the set of well densities n which satisfy the condition that at n the profit is less than f, less than or equal to the should be, and at 2n it is less than or equal to f. Did I say less than? Did I say that? Anyway, this is what I mean. Okay. All right. So those are equilibrium well densities with entry. Otherwise, people will exit. Sellers will exit. So I claimed up here that equilibrium is efficient. What do I mean by that? I mean basically that if you could basically be the social planner and you could dictate where all the wells were going to be, how many wells there would be, what the well density would be, then the well density that the social planner would choose is the well density that will happen in equilibrium. Okay. In other words, so what are we talking about efficiency here? What is the trade-off? So basically the trade-off is between digging another well, which means that you incur a fixed cost, right, and reducing the transport cost. Because if you have more wells, higher well density, then on average water has to be transported lesser distances, so you don't incur those losses from water transport, right. On the other hand, you pay a fixed cost. So there's a trade-off basically between these two kinds of costs. Yeah. Well, it's just saying that the incentive for a firm to enter in order to maximize its own profit leads to a situation in which costs are minimized. Total costs between fixed costs of digging a well and costs of transporting water are minimized. So that's the sense in which this is the allocation that a social planner who tried to minimize costs would choose. I'm not taking into account in so far. I'll talk about depletion later, but very soon. but I'm not. But I haven't got there yet. Okay. So this is statically efficient only in the sense that it minimizes the static cost allocation between the amount of fixed cost you incur in digging wells and installing pumps and in transporting water. Right? The more well density, the less water you have to transport. But the more the well density, the more cost you incur digging those wells. Okay. So just very quickly, why is it true that this situation is efficient? Well, a new seller like this guy at M, right? What's he going to get when he comes in? He's basically going to get the integral of the price path minus the cost path, right? Integrated over this area, right? Times the volume of water sold at each farm. And we assumed in the previous slide that that was constant. The volume of water sold is constant, is it? Perfectly inelastic demand. Okay. So basically this guy will come in if essentially this area times Q bar, which is the fixed quantity of water, is at least F. Okay. And how many of him are there? There are n of them, right? One at each midpoint. Okay. On the other hand, what does the social planner want to do? Social planner will decide, well, given that we're starting with n wells, right? The choice is whether to double the number of wells or not, right? So if you double the number of wells, you're going to incur a total fixed cost. So society is going to incur a total fixed cost of NF, right? And what is the cost saving from that NF? Well, where are the costs going to be saved? Well, from here to here up to this point, water is still going to be transported from this well to the farm, right? Because this is the least cost seller. It's only from here to here that where before the water was being transported from this well to a point like this, it's now going to be transported a shorter distance from here to here, right? And therefore, there will be a lower cost. So the cost saving is basically, again, is simply the area of these two multiplied by the quantity of water, right? So whether or not a social planner the condition for a social planner deciding whether or not to double the number of wells is exactly the same condition that private players will face when they decide whether to enter or not. The result is whatever the market outcome is, it's going to be what a social planner would have chosen. So that's statically efficient in that case. Now let's look at the case when wells are mobile and demand is still, we look at perfectly inelastic demand. What do I mean by wells are mobile? What I mean is that only a small portion of the fixed cost, so we can ignore it, comes from actually digging the well. Most of the fixed cost comes from buying the pump, let's say, and getting the electricity connection and so on. In that case, whenever there's new entry, right, whenever a new enters and starts selling water, all the other farmers will shift the location of their wells to adjust their location optimally. All right, so you can have the well density increase 1 unit at a time. And what can we say now about efficiency? So consider the case of inelastic demand at quantity Q bar as before. The efficient level of entry is given by minimizing the total cost of supplying water at marginal cost, which is this expression. It's quantity times the marginal cost at X integrated over all the X's for a given farm, doubled, and then multiplied by the number of farms, right? Plus the fixed cost of N wells. Okay, so you minimize that expression, and this is the solution. Okay, the optimal N, O for optimal, is given by this expression. So it's increasing in the amount of water supplied in the transport cost, and it's decreasing in the fixed cost, which is natural. What is the equilibrium entry? Equilibrium well density. It's the largest integer less than or equal to n star, where the profit at n star is equal to f, because as the well density increases, prices fall, profits fall, right? After profits, when well density increases up to f, then beyond that point entry will stop. There won't be any new wells, new sellers coming in. And this expression basically gives you this equation, right? Profit has to equal the fixed cost. Substituting for this price path, which is those blue lines and red lines I showed you, which is this equation, this is what the equilibrium well density will be. And if you compare it to the previous one, with the optimal one, you had a 4 here instead of a 2. So the equilibrium well density is greater than the optimal well density, right? More wells are dug than would minimize total costs in equilibrium. All right. So if you draw those two curves, basically this is the total cost, this is the profit, and it's essentially where they cross these fixed costs that you get these optima, which is that's the optimal one, and this is the equilibrium one. This is the equilibrium one, which is greater, this intersection and that intersection. And you can also calculate using that formula. The number of efficient wells is approximately 70% of the number of wells in equilibrium, and this is really happening because when somebody enters, they are kind of stealing business from the other competitors. Okay, just one remark here. Under inelastic demand, which is what we've assumed so far, taxing pumping costs has no effect on entry, right? Because there's perfect pass-through of prices to the consumer. I'll skip this also, nonlinear transport costs. Okay, let me just talk about quickly the static model with mobile wells. I'm going to stick to mobile wells now, and downward sloping demand for water. Okay, so this is here it's exactly as it was before. You have this expression for profits, price minus marginal cost times quantity integrated, that is one seller's profit. You can solve here. By the way, this is no longer true. I shouldn't say profit is independent of pumping cost. It's the markup here on the price that's independent of pumping cost. Profit does depend on pumping cost because an increase in the pumping cost raises the price, which reduces the demand now, right? Because now there is an effect on the quantity demanded. So what we can prove is the following result, and this is you have to go through some work to get this, but eventually, basically equilibrium entry is still higher than optimal provided demand is sufficiently steep. Okay, so remember we got this result that equilibrium entry was socially inefficient. There was too much entry, too much well density relative to what would minimize costs. This is still true if demand is sufficiently steep. Okay, The higher than optimal well density is accompanied by lower prices. That's what we saw, right? If there are more wells, basically your nearest competitor is nearer, that forces you to lower your price in this Bertrand framework. Therefore, because you lowered the price, now more water is used, because now we are assuming the general case when there's downward sloping demand. So far we've considered only a static model, and the inefficiency is entirely one of a failure to minimize the sum of fixed and transport costs. But note that in a dynamic context, there's an additional reason for reducing water use, right? In a dynamic context, all of these decisions are being made without taking into account the fact that every time I pump a cubic meter of water, I'm going to have less water in the next period. Now, if I have more water this period and less water next period, that means the marginal value of water is higher next period than this period, right? And because I'm not equating those marginal values properly discounted at some discount rate, right? Because I'm not taking that into account when I'm making my decisions here, I'm basically going to extract water too soon. Okay? So period to period, I should really be waiting. I should be taking the stock effect into account, but I'm not doing it. So there's a dynamic inefficiency which is there in addition to the one that we talked about, the static allocational inefficiency. And the dynamic inefficiency is what most of the literature is worried about, because that's the depletion issue. All right? And it can manifest itself in two ways. It can manifest itself simply in the way that, look, next period there'll be a shortage of water. Right? Water is scarce, marginal value water is higher, so it would have been efficient to transfer some of that water you use today, save it, and use it tomorrow instead when its value is higher. Some of them are just single decision maker optimization model. Most of the literature is not in a context in which there are any sales. Why is that? Because most of the papers were written in America, and each farm is thousands of hectares, right? And it has hundreds of wells, right? So there's no trade, right? But in South Asia and in North China, plot sizes are very small. Population density is much higher, and so a well on one farm can serve many farms. And so there's bound to be water trade. So those models haven't looked at water markets. So now let's just suppose for a minute that depletion only affects the water stock. It doesn't affect the cost of pumping. Right now, normally you would expect depletion to affect the cost of pumping. Why? Because you have to go deeper down to get the water, and therefore it takes more energy to pump it up to the surface, and more energy is higher cost. But if you're just paying a flat rate for the pump and you're not paying for the additional electricity that you use, then more energy is not higher cost. It's the same cost. Okay? So what happens in this situation is basically, as far as the farmer is concerned, depletion affects the available amount of water as far as he's concerned, but it doesn't affect the cost of pumping. That's C. It doesn't affect C. The cost of pumping it to the surface. Okay, so suppose next period available water is less than last period. Okay, now I want to explore the dynamics of this. Then aggregate supply, because aggregate supply must equal aggregate demand, therefore prices have to rise because supply has shrunk. Okay, quantity therefore declines, and because prices rise, profits approach monopoly profits. Profits go up, right? But the rise in profits is going to attract more entry, right? Higher well density. So ultimately this process leads to monopoly. You move out of the Bertrand regime into a monopoly regime. Okay, so here's what's happening. There's scarce water, right? In order to equilibrate supply and demand at any given farm, at any given location, the price has got to rise because there's less water available, right? So the prices rise. But if the price rises, then by this no arbitrage condition, right, prices have to rise exactly in this pattern, right? Because otherwise a farmer can sell water to the next farmer, right, at transport cost T. Everybody has the same transport cost. So prices have to rise exactly in this way. What happens? Eventually, if the scarcity gets steep enough, this price will rise to the point where this C plus T 1 by N will exceed the monopoly price, right? At that point, as a seller, I'm no longer constrained by my neighbor's competition. I'm constrained by the fact that if I raise the price further, my profit will actually fall because the demand from the farmer will fall enough that it doesn't compensate me for the rise in price. Okay? Now then the price path takes this form, right? It increases. Why? because the monopoly price is always an increasing function of marginal cost. Markup on marginal cost, and marginal cost increases as you move away from the wellhead because of the transport cost. Right? So this is what happens. You move into a monopoly, a territorial or spatial monopoly close to the wellhead, and this part is still Bertrand, it's still in the Bertrand regime. Further shortage of water then implies that the area between any two wells will not receive. So basically as there's further scarcity, prices will have to rise here also. Essentially what will happen is that this entire this curve will extend out to there, and this line will extend out to there, and the Bertrand regime will vanish. Okay, it's complete monopoly all the way up to here, right? I'm no longer constrained by my competitor's cost, I'll be constrained by the monopoly price. And if there's still further scarcity, right, at that point I can't increase profits by raising prices anymore. All that will happen is that since I'm making the least profit at the furthest distance where the cost is highest, I'm just going to stop supplying water to those guys. So essentially the farms here, the farms at the midpoint will stop receiving water, right? These will dry up. They'll go back to dryland agriculture. And the dryland agriculture zone will sort of spread outwards from this midpoint as the water scarcity gets worse and worse. Only farms close to the wellhead will get water. That's really the logical culmination of this process. Highest entry occurs with complete monopoly. Beyond that, profits start declining because the furthest farms don't get water. By the way, in this entire process, profits are going up, right? Profits are going up because prices are going up. The fact that profits are going up means that more people will enter. Okay, so in this situation, you get a boom. And when do you get a boom? You get a boom precisely when the available water is disappearing. This process, of course, ends at a particular point. At a particular threshold, no firm can cover fixed costs, and there's no water supply. It's the end. Right, that's the end. So here's as a function of well density as a function of water supply. Basically, with abundant water above some W bar, you're in that Bertrand regime, no problem. Okay. Well density is independent of the water stock. Okay, it's just a function of the transport cost T, the fixed cost F, and the demand curve. Okay, it's not related to supply. When scarcity starts to bite, then prices rise, profits rise, and therefore entry occurs, so well density goes up. And it keeps going up until it reaches that peak. That peak is when there's complete monopoly, and then well density falls. Well density falls because now profits are falling, right? After all, there's only enough water to supply a smaller number of farms now, and therefore your profits are falling as the amount of water you can supply falls, because you can't raise the price anymore. You've hit the monopoly price. Until you get down to a point where below that water stock, it's not worth drilling a well at all. It's too expensive. So that's why in the title of the paper has the boom before bust. So if you have this kind of phenomenon where you are not constrained by the fact that as the water gets scarce and the water table starts to fall, your pumping cost goes up. And in this kind of electricity pricing regime, you are in fact not constrained by that factor. Your pumping cost doesn't rise because you're not paying the marginal cost of extracting the water. Let's consider the other case. The other case is when the cost of pumping does increase with depletion. This is the case in China, this is the case in West Bengal, this is the case in most places. Okay, here farmers pay per unit energy consumed. Prices will rise, but quantity will fall at each location. So what's happening is that as the water gets scarce, what's happening is the water table drops. Because the water table drops, now you are paying for energy cost, and therefore your pumping cost increases, right? Because your pumping cost increases, right, your demand is affected, right? And so your profit is actually going to fall, right? So there could be exit in this case. If demand is inelastic, your profit may not fall very much. It depends how much your profit falls. So basically this effect goes in the opposite direction, right? There is an effect which sort of depresses profits, and there's the previous effect which I discussed, which raises profits as water gets more scarce. All right. So there are two competing effects. Things could go either way. It depends on the strength of the effects, right? Normally you would expect this effect, which is the cost effect, to prevail. But water stock is declining at the same time, and at a sufficiently low level of the water stock, as you reach basically the bottom, then you might get this boom effect right at the very end. I think I should stop here. I could just say very quickly. In some places, basically, this transport cost is not, those transport channels are not open channels, but you use sort of PVC pipes. In that case, you've done away with the seepage cost, and the pipe is simply a fixed cost. In that case, what you're going to get essentially is a bunch of spatial monopolies. The reason is everybody will try to buy the highest capacity pump possible so that you can supply to the largest area possible through these pipes. All right, there's no transport cost, so nobody is going to come in and compete with you, because if to come in and compete with you, they have to incur a fixed cost of digging a well, right? But how are they going to cover that fixed cost? Because you can always drop your price to marginal cost. You're already there. Your fixed cost is sunk. Okay, so there's complete entry deterrence. In this situation, you had a series of spatial monopolies. More wells implies faster depletion. So higher well density implies faster depletion because it lowers prices, therefore it increases water use. One thing that we don't have in our model, it's kind of easy to put in though, is, by the way, I have to say that I'm talking about a paper that hasn't been fully written yet. So it's very much work in progress, and I'm very happy to hear your comments on it, which direction you think we should take it. So one of the issues is really the equity issue. So it's typically, if you go around and you look at any of these farms and who's pumping water, you'll find that the guys with the wells and the pumps are the richer farmers. Right? On average, the ones who have access to capital at cheaper rates are going to be the richer ones, and therefore they are the ones who are going to be in a position to invest. Right? So the sellers are typically richer than the buyers. So there is an equity issue here. Poor people, poorer farmers who can't afford to dig their own wells are typically going to be buyers. Right? So they benefit from lower prices. Right? It's the richer farmers that benefit from higher water prices. But there's a trade-off with efficiency, which is that basically if you have lower prices, then of course there's going to be greater water use and faster depletion. Right? So there's an intertemporal problem, which is that it's good for the poor today to have lower prices, but it may be very bad for them in the long run because you're going to deplete faster. I think I'll basically stop there. So the essential issue is, as we saw, the market equilibrium here leads to a couple of things which are not good. One is that the allocation of wells, the number between wells and transport costs is likely to be suboptimal. There are likely to be too many wells. And the second thing is in the Bertrand case with the positive transport cost. And the second thing is that this is without taking the depletion externality into account. You take the depletion externality into account, you want less water being consumed. But today, less water being consumed is going to hurt the poor unless you can somehow change this distribution of access to wells, unless you can somehow intervene in the pricing market. But the way things are now, there is this trade-off. I'll stop.